Welcome to Lecture 3, Projectiles and Circular Motion. The dot point specifies that you need to be able to analyse theoretically and practically the motion of projectiles near the Earth's surface, and that you need to be able to have a qualitative description of the effects of air resistance, which means that you will not be required to do any calculations involving air resistance. I have identified all of the questions from the last few years' papers that are involving projectile motion, and within that categorisation I've tried to refine the definition of the type of idea that's being tested in a little bit more detail. I have categorised the questions depending on how they were launched, either vertically, horizontally or obliquely, and how they would land either at the same height or at different heights. The other ideas that you need to understand is how to find the height, the maximum height most commonly, the range, and the time of flight. You also need to be aware of what's happening with the energy throughout the motion, and you also need to be able to consider the effects of air resistance. The solution process depends on how the projectile was launched. So we will consider 4 different types: when it is launched vertically, when it is launched horizontally, when it is launched obliquely and lands at the same height, or when it is launched obliquely and lands at a different height. The first type of projectile problem is when it is launched vertically. The acceleration is going to be 9.8 meters per second squared down. You will use an equation to find how long it takes to get to the top, because at the top the velocity will be equal to 0. Or you might use that time that you've discovered there to work out how high it goes. Then you might be asked to find the time of flight if it returns to the original launch height, or if it falls further and lands at a different height. Basically, they will just be using equations of motion, accelerations g, and you will solve for the unknown variables. The second type of projectile motion is when it is launched horizontally. Again, the acceleration down will be 9.8. We will divide the problem into 2 parts, horizontal and vertical. In the horizontal direction, the acceleration is 0, so the velocity is constant. So the distance travelled is given by the initial horizontal velocity times the time it takes to fall. You will find the time it takes to fall by considering the vertical direction. You will usually be told the height it's falling from, and you will use x is equal to ut plus a half gt squared, where u is 0, to find out how long it takes to fall. Once you know how long it takes to fall, you will use that time to get and find the range that it travels. You will always use the time to move from a horizontal direction into a vertical direction, because the time is constant. If the launch is at an angle, then you need to resolve the initial velocity into its 2 components. One which is the horizontal component, which is v cos theta, and the vertical component, which is v sine theta. Projectile problem type 3, where it is launched at an angle but lands at the same height. This flight will be symmetrical. The acceleration will be g, which is 9.8 meters per second squared down. You divide the problem into 2 parts, horizontal and vertical. In the horizontal, the velocity is constant, so the distance travelled is given by the initial horizontal velocity, which is v cos theta, times the time t. In the vertical, we're going to consider what's happening on the way up and what's happening on the way down. On the way up, it has an initial velocity of v sine of theta, but a final velocity of 0. So use that to find out how long it takes to get to the top, and you can then use that to find out how far it has travelled when it gets to the top. If we know how long it takes to get to the top, Then we can double that to find the time of flight. Once we know the time of flight, we can actually then just find that, use that to find how far it travels, to find what its range is. If there is no air resistance and the flight is symmetrical, you can use the range formula, which is the range is equal to v squared sine of 2 theta over g. I caution you in using this formula because it is often misapplied. The final type of projectile motion we need to consider is when it's launched obliquely and it lands at a different height. The methodology is the same as before. We're going to treat it as horizontal and vertical. In the horizontal, the acceleration is 0, so the distance travelled is the velocity times the time. In the vertical, we're going to find the time it takes to reach the top. We find the height it gets to. Then if we add that to the launch height, then we can actually find out how long it's going to take to fall. Or we can use y is equal to ut minus a half gt squared if we know how long it's going to take to get to the end, and then substitute in for t into that equation. If the value for y is negative, then that just shows that it is below the launch height. That tells me the distance below the launch height. The next video shows us what projectile motion looks like if we're in a stationary frame or if we're in a moving frame. And the second video shows us what happens with projectile motion if we don't take air resistance into consideration.
Projectile motion. This cart travels on an almost frictionless track. A trigger mechanism in the base of the cart can be used to release a compressed spring. As the spring expands, its restoring force can push a projectile up and out of the funnel of the cart. A heavy steel ball makes a good projectile for which air resistance is negligible. A metal clip halfway down the rail can be used to activate the trigger mechanism on the cart. Once it leaves the spring, the only force acting on the ball is the vertical force of gravity. In the laboratory frame of reference, a projectile ejected from the cart moving in a constant horizontal velocity will travel in a parabolic path under the influence of the vertical gravitational force. If we observe this event in the frame of reference of the cart, by moving the camera at the same velocity as the cart, the projectile has no horizontal velocity component. In this frame of reference, the projectile moves only vertically under the influence of gravity.
Circular motion. There is a fair bit in circular motion. You need to be able to use F is equal to mv squared over r. You need to apply it to three particular types of problem: a vehicle moving around a circular road, a vehicle moving around a banked track, and an object on the end of a string. You also need to be able to model artificial satellites as being circular motion, and you need to investigate Newton's second law with vertical circles, but we only need to consider the forces acting at the highest and the lowest points. I have grouped the circular motion problems into a range of categories. The first one is we need to consider horizontal circles, then we need to be able to apply F net is equal to mv squared over r. We need to consider vertical circles, banked curves, conical pendulums, the normal reaction in vertical circles, and also satellites in circular motion. Horizontal circular motion. Up until now in the course, The direction of the force has always been constant, therefore the direction of the acceleration has been constant. So we've been able to use equations of motion based on constant acceleration. This is the first case where the direction of the acceleration isn't constant. The magnitude can remain constant, but the direction is changing. So our equations of motion are no longer useful. For a horizontal circular motion, the direction of the net force is always perpendicular to the direction of the motion of the body. This is an important definition for later on in the course in light and matter. The formula we're going to use for the force is that F is equal to mv squared over r, and that the acceleration is equal to v squared over r. You also need to understand that the direction of the force is always radially inwards, vertical circles. The study design states that we only need to deal with problems involving bodies at the top and at the bottom of the vertical circle. Let's consider the top. The two forces acting are the normal reaction force plus the weight. They're both acting down. They're going to sum together to give me the net force, which is going to be N plus mg. Because it's moving in a circle, it's going to equal mv squared over r. I set the equation up and I solve for the unknown at that point. At the bottom of the circle, the two forces acting are the normal reaction force and the weight, but they're in opposite directions. The net force needs to be radially inwards, so that means that the equation needs to be the normal minus mg is equal to mv squared over r, because the normal needs to be greater than mg so that the net force is radially inwards. Banked curves. You need to be particularly careful looking at these diagrams. They look similar to the diagram for an inclined plane. The problem is, in an inclined plane, the direction of the acceleration is down the slope. In a banked curve, the body is moving in a horizontal circle, so the direction of the net force is radially inwards. Therefore, we resolve the normal reaction into one that is vertical and one that is horizontal. The vertical component will be equal and opposite to the weight, and the horizontal component, n sine theta, is the unbalanced force, which is going to give rise to the net force, which is mv squared over r. We can actually use that the normal force, n cos theta, is equal to mg, and that mv squared over r is equal to n sine theta. If we rearrange those, we can get the formula that tan of theta is equal to v squared over rg. This is a really useful formula and should be on your cheat sheet, but be very careful making sure that you understand this formula only works for banked curves and for conical pendulums. Conical pendulums. When we look at the force diagram for a conical pendulum, it is going to give rise to a net force being radially inwards. So we are going to resolve the tension into a vertical component and into a horizontal component. The vertical component T cos of theta is going to be equal to mg in magnitude, and the horizontal component T sine of theta is going to give rise to the net force, which is mv squared over r. Again, rearranging those formulas and combining them, we can get that tan of theta is equal to v squared over rg. Again, a useful formula, but you must understand it only works for banked curves and conical pendulums because they are basically the same. Your weight is the force of attraction of the Earth on you. Your apparent weight is the upward normal or reaction force. This force can vary depending on your acceleration, because you feel how hard the floor is pushing on you, not how hard you're pushing on the floor, because you're not the floor. You can only feel forces that are being exerted on you. If you were the person swinging on a swing or moving in a vertical circle, at the bottom of the vertical circle you are going to feel heavier, because the normal reaction force is going to be greater than mg. If you were travelling in a vertical circle and at the top, you are going to feel lighter, because the normal reaction is going to be given by mg minus mv squared over r. If you are going fast enough, then the normal reaction is 0, and at this point you will feel apparently weightless. We're told that the ball is launched from a height of 58, and we want to find when it hits the ground. So we set this equation up with x is equal to minus 58. We know u is 15 because that's going to be up, and we know g is minus 9.8. Put that into v squared minus u squared is equal to 2gx, and we get that the final velocity is going to be 36.9 meters per second. We then can put that into v is equal to u plus gt, and we're going to get that it takes 5.30 seconds to land. We know that the velocity of the ball is going to be 0 in the middle of its flight because it comes to rest. We also know that the velocity is initially going to be in one direction and finally in the opposite direction, so the velocity must change from being either positive to negative or negative to positive. We also know that the acceleration due to gravity is going to be constant and negative. Therefore, the answer has to be D. The horizontal velocity is going to remain constant. We are told that after 2 seconds that the velocity is at 45 degrees, which means the horizontal component and the vertical component must be the same, which means that the velocity must be root 2 times u, the initial horizontal speed. If we consider the vertical direction, after 2 seconds, the vertical component is going to be 19.6 meters per second. So the horizontal component is 19.6. So the actual magnitude of the vector at 45 degrees is the square root of 19.6 squared plus 19.6 squared. That gives me the answer D. With horizontal projectile motion, the time it takes to fall is given by x is equal to ut plus a half at squared, but u is 0 because in the vertical direction the initial velocity is 0. Substituting in gives me t is equal to 1 second. Once I know the time is 1 second, then the range is just going to be 6 times 1, which is 6 meters. Since both paintballs reach the same height, they must take the same time to get there because the acceleration remains constant, which means that the time to the top is the same, so the time back down is the same, so the time of flight will be the same. Therefore A and C. B can't be right because in the same time it needs to travel a lot further, so the speed must be greater and the angle must be less. The total energy remains constant. At launch, the gravitational potential energy is 0, so the kinetic energy is the total energy. Therefore, the kinetic energy must be T. The answer is A. This is a difficult question. We're going to use a technique of eliminating all of the answers and see what's left. Not one I like, but sometimes we need to do it. Option A is incorrect because the object is still moving at the top, so it has kinetic energy. Option E is incorrect because it's actually the difference between two energies, which is an energy. We're looking for velocity. At the top, the total energy is the kinetic energy plus the gravitational potential energy. We can't just use the total energy, so we need to eliminate B. Option C, the momentum is going to change in the vertical direction. The horizontal momentum is going to remain constant, so that's not going to be correct. Option D, which is where we're finding the kinetic energy, well, the kinetic energy is going to change depending on what point we're at, so that can't work. Therefore, the answer has to be F. The horizontal component of the velocity will remain constant at 20 cos of 30, which is 17.32 meters per second. The vertical component of the velocity is going to change, and after 2 seconds it will be 20 meters per second. Using Pythagoras gives me that the velocity is 26.45 meters per second after 2 seconds. Then using trig to find the angle to the horizontal gives me the tan of theta is going to give me the angle of theta is 49.1. We probably can only quote our answer to two sig figures, so the best answer is that the velocity is 26 meters per second and that the angle is 49 degrees to the horizontal. You need to specify a direction to solve this question. Typically you will set up as being positive. Then we know the elements that we've got to deal with. We used the acceleration is minus 10, the initial speed is 30 meters per second up, and the time is 9 seconds. If we put that all in, we're going to get that the height after 9 seconds is minus 135 meters. That means that the cliff was 135 meters higher than when it landed. Therefore, H is 135 meters. This question only requires us to consider the vertical components of the velocity. At the top, the vertical velocity is 0. So if we use v squared minus u squared is equal to 2gx, substituting in, considering that the initial vertical velocity is 30 sine of 36.9, and then we can substitute in and we get x is equal to 16.2 meters. The stem of the question tells us to ignore air resistance. Therefore, the only force acting on it will be the weight force down, giving an answer R. The simplest way to solve this problem is to find the time it takes to reach the advertising board if it was just going horizontally, and then to find its height at that time. Using the horizontal direction, we find that the time it takes to hit the board is 3 seconds. So in the vertical direction, we're going to get that the height is 9 meters. Newton said that an object would remain at rest or in uniform motion unless a force acts on it. When the string breaks, the force that was acting on the object making it travel in circular motion no longer exists. Therefore, it's going to take off at a tangent. Therefore, the answer is A. The car is travelling in a horizontal circular path. That means the net force must be radially inwards. The force is a vector. So the two forces that are acting, the air resistance and the driving force, must add together to give a vector that is radially inwards. The only one that does this is option E. This is what I call a simple plug and play question. Substitute the numbers in, use the appropriate formula and come up with an answer. You're going to use F is equal to mv squared over r, and you're going to find that the force was 2,560 Newton. At the bottom of a vertical circle, F net is equal to the normal reaction minus mg. We know that mv squared over r is equal to n minus mg. Rearranging gives me n is equal to 38 Newton. When the question states that you may include a diagram, I think you should take it as assumed that you should include a diagram. Draw the diagram at the top and at the bottom. At the top, the two forces acting, the weight and the tension, are both acting down, so F net, which is mv squared over r, is equal to T plus mg. You can rearrange that to write that T is equal to mv squared over r minus mg. At the bottom, F net is equal to T minus mg. If you rearrange that, you get T is equal to mv squared over r plus mg. So the difference between the tension at the top and the bottom is actually equal to 2 mg. The question says draw the two forces acting and then label the net force. I think you should label all forces acting and be careful where you draw your labels so that it's clear which one you are talking about. The two forces acting is the weight acting straight down and the normal reaction acting perpendicular to the surface. They combine together to give a net force which is radially inwards, and that should have been labelled sigma F or F net. If you have the formula tan of theta is equal to V squared over Rg on your cheat sheet, then this question is an incredibly easy question to do. Substitute in and get 7.1 degrees. This is a conical pendulum problem. The net force is radially inwards. There are two forces acting. There's the tension and the weight. Draw them in the correct directions, label them, and make sure that your net force is labelled and it is a dashed line as was required. The simplest way to solve these is to consider it as a horizontal problem or a vertical problem. If we consider this as a horizontal problem, then the net force acting on it is T sine theta in the horizontal, and that should equal mv squared over r. We know all of those variables except for T. Substituting in gives me T is equal to 23.1. The other way is to consider the vertical direction. It's not moving in the vertical direction, so the net force is equal to 0, which gives me that T cos theta will equal mg. Again, substituting in gives me 23.1 Newton. Possibly the easiest way to do this is to consider when would the motorcyclist lose contact with the surface, and that's when the normal force is equal to 0, which was when mv squared over r is equal to mg, which is when g is equal to v squared over r. If we substitute in, we get v is equal to 5.94, so the best answer is C. Our definition for circular motion is when the net force is acting radially inwards and it is at right angles to the velocity. The only situation that describes this is diagram A. The next slide is a movie demonstrating circular motion and projectile motion. It's not for the faint-hearted. If you happen to be a cat lover, please stop the video now.
Miffy! Miffy, come here! Turn off the fan!